To give the presentation of organic chemistry on the topic of alkyl halides. Introducing to alkyl halides. Alkyl halides are organic molecules containing a halogen atom bonded to an sp3 hybridized carbon atom. Alkyl halides are classified as primary, that is 1 degree, secondary, that is 2 degree, and tertiary, 3 degree, depending on the number of carbon bonded to carbon with the halogen atom. The halogen atom in halides is often denoted by the symbol X, where X can be any one: chlorine, bromine, fluorine, iodine. There are other types of organic halides. These includes vinyl halides, aryl halides, allylic halides, and benzylic halides. Vinylic halides have a halogen atom bonded to a carbon-carbon double bond. Aryl halides have a halogen atom bonded to a benzene ring. Allylic halides have X bonded to the carbon atom adjacent to a double bond C carbon-carbon double bond. Benzylic halides have X bonded to the carbon atom adjacent to a benzene ring. So, here are the examples of 1 degree, 2 degree and 3 degree alkyl halides. This is 1 degree iodine, 2 degree bromide and 3 degree chlorine. As in first, you can see that iodine is connected with carbon, which only connected with one carbon. And in 2 degree bromine, bromine is connected with that carbon which is connected with two other carbons. And in 3 degree, we can see that chlorine is connected with that carbon which is connected with other 3 carbons. Now let's see 4 types of organic halides having X near a pi bond. sp2 hybridized carbon. Here we can see vinyl halide in which C double bond C, X is connected with this carbon which is sp2 hybridized carbon. And aryl halide, here is a benzene ring and X is directly connected to it. Now sp3 hybridized carbon. Allylic halide, here the X is connected with that carbon which is adjacent to carbon double bond carbon. And in next also X is connected with that carbon which is adjacent to the benzene ring carbon. Let's move ahead. Now see nomenclature. Name of an alkyl halide using the IUPAC system. Let's see example. Here is the example given. Now let's see how can we write its name. Step 1. Find the parent carbon atom containing the halogen. Here, name the parent chain as an alkane with the halogen as the substituent bonded to the longest chain. Firstly, we have to find the longest chain, where any X atom, that are halogen atoms acting as a substituent. Next step, apply all other rules of nomenclature. Begin at the end nearest the first substituent, either alkyl or halogen. B. Name and number the substituents like methyl at C5, chloro at C2. C. Alphabetize. C for chloro, then M for methyl. So answer is 2-chloro 5-methyl heptane. Now let's move ahead. Common names are often used for simple alkyl halides to assign a common name. Name all the carbon atoms of the molecule as a single alkyl group. Name the halogen bonded to the alkyl group. Combine the names of the alkyl group and halide separating the words with a space. Common names are, firstly here we see tert butyl iodine, and the next is ethyl chloride. Its IUPAC name is chloroethane. Physical properties. Now let's see the physical properties of alkyl halides. Alkyl halides are weak polar molecules. They exhibit dipole-dipole interactions because of their polar carbon bond with X. But because the rest of the molecules contains only carbon bonded with carbon and carbon bonded with hydrogen bonds. They are incapable of intermolecular hydrogen bonding. So here we can see dipole-dipole interactions. Opposite end of the dipoles interact. Physical properties of alkyl halides. Boiling point and melting point. Let's see. Alkyl halides have higher boiling points and melting points than alkenes, having the same number of carbons. Let's see the example of ethane. The boiling point is minus 89 degrees Celsius and the boiling point of bromoethane is 39 degrees Celsius. Boiling points and melting points increases as the size of R increases. R represents alkyl group. So the melting point of chloroethane is minus 136 degrees Celsius and boiling point is 12 degrees Celsius. And chloropropane is melting point is minus 123 degrees Celsius and boiling point is 47 degrees Celsius. Larger surface area, higher melting point and boiling point. Now let's see, melting points and boiling points increases as the size of halogen atom increases. As we can see in this example, chloroethane melting point is minus 136 degrees Celsius and boiling point is 12 degrees Celsius. And in case of bromoethane, melting point is equal to minus 119 degrees Celsius and boiling point is 39 degrees Celsius. More polarizable halogen, higher melting point and boiling point. Rx is a soluble in organic solvents. Rx is insoluble in water. Here was the solubility factor. Now let's see general features of nucleophilic substitution. Three components are necessary in any substitution reaction. General substitution reaction. Rx plus nucleophile is equal to R bonded with nucleophile plus X negative. Here we see sp3 hybridized carbon bonded with halogen group and then the nucleophile reacted with it and formed R bonded nucleophile, and here the leaving group is X negative, which is halogen. For example, chloromethane plus hydroxide ion is equal to methanol plus leaving group is chlorine. Second, CH3CH2CH2I plus SH negative, which is thiol group. It is equal to CH3CH2CH2SH plus leaving group is iodine here, iodine ion. Third example is CH3CH2Br when reacted with OCH3 negative. Here we find CH3CH2OCH3, which is a ether, plus Br negative ion left. Negatively charged nucleophiles like hydroxide and HS negative are used as salts with lithium positive, sodium positive and potassium positive containers to balance the charge. Since the identity of the container is usually inconsequential, it is often omitted for the chemical equation. Here is a chemical equation given: CH3CH2CH2Br. Bromopropane is reacted with NaOH, which converts into CH3CH2CH2OH plus NaBr. When a neutral nucleophile is used, the substitution product bears a positive charge. So let's see a reaction. When CH3CH2CH2Br is reacted with neutral nucleophile, that is NCH3 whole thrice, it is equal to CH3CH2CH2 N positive CH3 whole thrice plus Br negative. Furthermore, when the substitution product bears a positive charge and also contains a proton bonded to O or N, the initially formed substitution products readily loses a proton in a Bronsted-Lowry acid-base reaction, forming a neutral product. So let's see here the example. When CH3CH2CH2Br is reacted with ammonia, it converts into CH3CH2CH2 N positive with 3H. It goes When NH3 is reacted again, then it is converted into CH3CH2CH2 NH2 plus NH4 positive. In step 1, nucleophilic substitution plus Br negative. Step 2, proton transfer is seen. The overall result is a neutral product. To draw any nucleophilic substitution products, find the sp3 hybridized carbon with the leaving group. Identify the nucleophile, the species with a lone pair or pi bond. Substitute the nucleophile for the leaving group and assign charges to any atom that is involved in bond breaking or bond formation. Second, bond breaking occurs before bond making. Two steps in mechanism. In this example, as we can see, this bond is broken before the next bond is formed with nucleophile. So from here we can confirm that thing. In this scenario, the mechanism has two steps and a carbocation is formed as an intermediate. Because the first step is rate determining, the rate depends on the concentration of Rx only. That is, the rate equation is first order. Third, bond making occurs before bond breaking. So let's see. In this example, we can see that when the nucleophile attacks on this carbon, the bond is broken after the bond is formed with nucleophile. This mechanism has an inherent problem. The intermediate generated in the first step has 10 electrons around carbon, violating the octet rule. Because two other mechanistic possibilities do not violate the fundamental rule, the last possibility can be disregarded. Here we can see a reaction where CH3Br plus acetate ion is reacted and it gets methyl acetate plus bromine ion. Kinetic data shows that the rate of reaction first depends on the concentration of both reactants, which suggests a bimolecular reaction with a one-step mechanism. This is an example of an SN2 substitution nucleophilic bimolecular mechanism. Consider reaction 2 below. Now let's see the next reaction. Second, CH3 whole thrice CBr plus acetate ion. It gets converted into CH3 whole thrice bonded with C and then O, C double bond O, CH3 plus bromine ion. From here, the rate is equal to K into CH3 whole thrice CBr, first order kinetics, because only one reactant appears in the rate equations. Kinetic data shows that the rate of reaction in second depends on the concentration of only the alkyl halide. This suggests a two-step mechanism in which the rate determining step involves the alkyl halide only. This is an example of an SN1 substitution nucleophilic unimolecular mechanism. Mechanism of an SN2 reaction. The curved arrow notations are used to show the flow of electrons. One step, the C bonded with Br bond breaks as the C bond with O bond forms. In this example, the acetate ion is reacted with bromomethane, the first step. So here, new CO bond formed, as we can see in CH3 C double bond O, OCH3 plus Br negative. An energy diagram for the SN2 reaction. In the reaction, CH3Br plus acetate ion is equal to CH3COOCH3 plus Br negative. So here is the energy diagram. So as we can see that CH3Br plus acetate ion has more energy, which means in comparison to the product, that is CH3C double bond O, OCH3 plus Br negative ion. It means that the product is stable than the reactant. In between that, we can see the transition state where one bond is breaking and one bond is forming, partially forming. So let's see it. In the transition state, the C bond Br bond is partially broken, the CO bond is partially formed, and both the attacking nucleophile and the departing leaving group bear a partial negative charge. Stereochemistry. All SN2 reactions proceed with backside attack of the nucleophile, resulting in inversion of configuration at the stereogenic center. In this example, we can see that nucleophile is attacking on the carbon, and then the transition state is formed, and then Br negative ion is left. Here we can see that the inversion of configuration is seen. Nucleophile and bromine ion are 180 gamma away from each other on either side of a plane containing R, H and D. The bond to the nucleophile in the product is always on the opposite side relative to the bond to the leaving group in the starting material. From here we can also see when SH negative attacks on this C, I is the leaving group from here, and inversion of configuration is seen. Again we can see one more example in which hydroxide ion is attacking on carbon and chlorine is leaving group here, and here is inversion of configuration. As the number of R groups on the carbon with the leaving group increases, the rate of an SN2 reaction decreases. As we can see, methyl 1 degree, 2 degree, 3 degree groups increase, and we can also see the direction of increasing rate of an SN2 reaction, because when इट इज़ लेस, जब CH3X जो है मिथाइल, उसके अंदर कोई भीड़ करने वाली कोई जगह ही नहीं है, तो जो भी न्यूक्लियोफाइल आएगा वो इजीली उसके ऊपर अटैक कर पाएगा और इन्वर्जन ऑफ कन्फिग्रेशन हो जाएगा और ये रिएक्शन बहुत इजीली प्रोसीड कर जाएगी. जब CR3 हमारे पास ये है तो उस टाइम पे काफ़ी भीड़ का एरिया होगा. ऑलरेडी ये न्यूक्लियोफाइल को आने ही नहीं देगा वहाँ पे और SN2 रिएक्शन को ईजिली नहीं होने देगा. Methyl and 1 degree alkyl halides undergo SN2 reactions with ease. 2 degree alkyl halides react more slowly. 3 degree alkyl halides do not undergo SN2 reactions. This order of reactivity can be explained by steric effects. Steric hindrance caused by the bulky R groups made nucleophilic attack from the backside more difficult, showing the reaction rate. The higher the EA, the slower the reaction rate. Thus, any factor that increases EA, that is activation energy, decreases the reaction rate. In this diagram, the same thing is given. A. CH3Br plus hydroxide ion reacts and formed CH3OH plus Br negative. CH3Br is an unhindered alkyl halide. The transition state in the SN2 reaction is lower in energy, making activation energy lower and increasing the reaction rate. B. Second example, here CH3 twice HBr plus hydroxide ion, it forms CH3 twice CHOH plus Br negative. CH3 twice CHBr is a sterically hindered alkyl halide. The transition state in the SN2 reaction is higher in energy, making activation energy higher and decreasing the reaction rate. Increasing the number of R groups on the carbon with the leaving group, increasing crowding in the transition state, thereby decreases the reaction rate. The SN2 reaction is fastest with unhindered halides. Here we can see less crowded transition state, lower in energy, faster SN2 reaction. More crowded transition state, higher in energy, slower SN2 reaction. Characteristics of SN2 mechanism. So let's see characteristics and result. First, kinetics. Second order kinetics. Rate is equal to K into Rx, concentration of Rx and concentration of nucleophile. Mechanism, that is one step. Stereochemistry, backside attack of the nucleophile and inversion of configuration at the stereogenic center. Identity of R. Unhindered halides react fastest. Rate is equal to CH3X is more than RCH2X is more than R2CHX is more than R3CX. Stereochemistry. To understand the stereochemistry of the SN1 reaction, we must examine the geometry of the carbocation intermediate. A carbon cation with 3 groups around C is sp2 hybridized with trigonal planar and contains a vacant p orbital extending above and below the plane. Loss of the leaving group in step 1 generates a planar carbocation, that is achiral. In step 2, attack of the nucleophile can occur on either side to afford two products which are a pair of enantiomers. Because there is no preference for nucleophilic attack from either direction, an equal amount of two enantiomers is formed, a racemic mixture. We can say that racemization has occurred. The rate of an SN1 reaction is affected by the type of alkyl halide involved. As the number of R groups on the carbon with the leaving groups increases, the rate of an SN1 reaction increases. From here we can see that 3 degree has the highest rate, then 2 degree, then 1 degree, and then methyl group. 3 degree alkyl halides undergo SN1 reaction rapidly. 2 degree alkyl halides react more easily. Methyl and 1 degree alkyl halides do not undergo SN1 reactions. This trend is exactly opposite to the observed in SN2 reactions. Characteristics of the SN1 mechanism. So let's see characteristics and result. Kinetics. First order kinetics. Rate is equal to K into concentration of Rx. Mechanism is two steps. Stereochemistry. Trigonal planar carbocation intermediate. Racemization at a single stereogenic center. Identify of R. More substituted halides react fastest. Rate is equal to R3CX is more than R2CHX is more than RCH2X is more than CH3X. Factors affecting SN1 and SN2 reactions. Four factors are relevant in pretending whether a given reaction is likely to proceed by an SN1 or an SN2 reaction. The most important is the identity of the alkyl halides. Increasing alkyl substitution favors SN1. Decreasing alkyl substitution favors SN2. Methyl and 1 degree alkyl halides undergoes SN2 reactions easily. 3 degree alkyl halides undergoes SN1 reactions only. 2 degree alkyl halides undergo both SN1 and SN2 reactions. Other factors determine the mechanism. The nature of the nucleophilic is another factor. Strong nucleophiles, which usually bears a negative charge, present in high concentrations favors SN2 reactions. Weak nucleophiles such as H2O and ROH favors SN1 reactions by decreasing the rate of any competing SN2 reaction. Let us compare the substitution products formed when the 2 degree alkyl halides A is treated with either the strong nucleophile OH negative or the weak nucleophile H2O. Because a 2 degree alkyl halide can react by either mechanism, the strength of the nucleophile determines which mechanism takes place. So here were some basics of alkyl halides, some types of reactions and how the reactions move. There were some mechanisms we read. So that's all for this presentation. Thank you.